Welcome back to EET 260 microcontroller applications, and we're going to talk about time of flight sensing, which you will do with your ping sensors and your basic stamp boards. What I have posted here, this will be posted on the Blackboard site, is this kind of summary of time of flight. Time of flight sensing has an underlying idea, and it's the basic principle behind radar, which is radio detection and ranging, sonar, sound navigation and ranging, and LiDAR, light detection and ranging. So, as you say, here's the basic deal. You've got some kind of transmitter here, and it's going to emit energy. And I showed some backward curves here because typically if you had some kind of a parabolic dish, you would have some kind of feed point here, and you would project energy into the dish, and then the dish would focus the energy out this way. But whatever you have some kind of transmitter that sends energy of some kind out to a target, and that target absorbs and retransmits. That is, it reflects some amount of energy back, and you receive the returning energy with a receiver. Now, if you look at this in the time domain, here we have the transmitter pulse, and it might be a burst of sinusoids, just a packet of waves here that's sent out, and sometime later we get a similar signal back on the receiver, although it's attenuated, obviously, because we're not going to get back all the energy we sent out. And so what we're really doing here is just your basic distance equals rate times time. If we use light or radio waves, the speed of electromagnetic radiation is the constant lowercase c. At least in free space, it's very close to 300 times 10 to the 6th, or 300 million meters per second. And the distance we're interested in is half of the distance covered during the time. This time of flight out here is actually a round trip time. It's the time when we emitted the pulse. So it had to travel out here, hit the target, come back, and be received. The distance equals rate times time equation then basically comes down to, we don't know the distance, but we do know the rate, and we're measured the time, and we know how to multiply by 1/2. So it's all pretty easy. If for example, if our radar return occurs after 193.6 microseconds, we would tend to think that the distance was the speed of light times 193.6 microseconds. Here's your 10 to the minus 6 seconds, microseconds, and of course this is 300 million meters per second, and we want half of that distance. So as we go down here, we see that 10 to the plus 6 and 10 to the minus 6 cancel. And also, it's a little bit hard to see, but the S is overstruck in the denominator here, and it's overstruck in the numerator up here. The seconds cancel, and we just get meters. And so the answer is 1/2 of 300 times 196, or 29.04 times 10 to the third meters, 29.04 kilometers, or very close to 15 miles. So, in a radar situation, we'd expect the target to be out there at 15 miles. Another example uses sound waves, which travel at about 1,100 feet per second at sea level, somewhere around there. I put a question mark in because it's, there's a lot of things, humidity, when you're going through the air with sound, there's a lot of things that affect it. Certainly elevation, humidity, temperature, all that. But let's say we detect an echo of our of a ping that we sent out after a round trip time of flight T sub f of 600 milliseconds. Well, of course here I have distance equals 300 times 10 to the 6th. I don't think that's quite right. And why don't we fix that right away? This will be 1.1 times 10 to the 3 feet per second. Fix that right now. This will be feet per second. And of course that's times whatever TF is. In our case it'll be 600 milliseconds. So here's D equals 1100 feet per second times 600 milliseconds. We want half of that distance because we only want the distance out. And once again we see that things cancel out, and we get that the distance is 1.1 times 600, so that's 660, times a half is 330. So our ping went out to about 330 feet. Now the ping sensors that we use with the basic stamp are not capable of that. And I believe those original ping sensors were developed as part of a autofocus system for the original Polaroid one-step cameras, like back in the early 70s or something like that, or late 60s and early 70s. So if you want to sense the velocity of a target, you get the position from that time of flight. But to get the velocity of the target, if you send out a burst of light or ultrasound or radio frequency or whatever, you will experience what's called the Doppler effect. This is when a train goes by and you get that sound, or the same thing on a race car dragway. The apparent pitch of the sound increases as it's coming toward you, then it drops as it's going away. And we'll take a look at why that happens when we'll look at the Wikipedia page. And there's a link here if you really want to learn about the Doppler effect and be able to calculate the change in frequency. You can do that. Now, if you have a multiple receiver system, then time of flight systems can be greatly enhanced by employing multiple receivers in an array of sorts. Such an arrangement allows the system to detect the return burst at a diversity of locations. So now you've got all sorts of information because you hooked up a whole bunch of receivers and you detected the time interval for the return burst at each receiver. Knowing the dimensions of the receiving array and some basic geometry and trig, one can ascertain the direction of the return burst. In other words, if I had three receivers and some of the receivers received the received burst later and others received it earlier, I would tend to think that the target was closer to the earlier receivers and farther from the later receivers. And you could quickly triangulate where the target is. So many radar and sonar applications use an array of receivers and not just one. But that goes beyond time of flight. I just wanted you to know what's really happening in microcontroller systems that use some of these technologies. Some are simply just looking for the distance to an object, but others are doing much more complicated processing. If you see that head end thing that they put on a pregnant woman when they're looking at the baby, that thing has a sender unit in it, and then it's got microphones all around that center receiver, and that goes into a computer, and they don't just get the time of flight and distance to parts of the baby. They can actually get the beating heart and everything. They can actually get enough information to make an image. The same thing for an electrocardiogram, where they can actually introduce an ultrasound source right into the heart, and then with a multi-receiver array outside the person, they can pick up and create a real-time beating heart image. So these radar systems, and the same kind of idea goes on to all these MRIs and PET scans and CAT scans. I mean, they use different techniques. They create the energy in different ways, but they all have multiple receivers and a ton of computing power to make compute what the image is, and they can even do focusing in the computer. So you in a military environment, you can actually get an image of what it is you're looking at out there, perhaps whether it's an airplane or size of the airplane or that sort of thing. So the military applications of time of flight are pretty well known, radar and sonar, and of course these nowadays tend to use more than one receiver, so that they get direction, they get distance, and by using that Doppler effect we mentioned and noticing that the frequency of the pulse they send out is a little different when they receive it, they can pick up the velocity of the object. All right. These location systems are enhanced to identify velocity of the object, and in the case of multiple receivers, are able to determine the direction from which the echo signal is coming, and even image the target. So in some cases they can image the target. So we have commercial applications of this. Fish finders are a basic echo type system that drives an ultrasonic burst into the water and listens for the response, and it's got some kind of graphical display, and depending on how much you spend on it, it either just gives you a depth, or it tells you if there's maybe you can figure out if you're hitting the bottom instead of finding fish or something. They have all sorts of features. Autofocus on cameras, surveying. Surveyors now use laser type systems to illuminate a target that someone holds, and the laser system on the tripod gives you a distance, coordinates with GPS, and it helps to find angles, like if you're looking down a slope or up a slope, or if you're level. So and with sonar you can do subsurface ocean floor mapping, and Robert Ballard, the guy who led the search for the Titanic and the USS Thresher and several other I think his people found the Freedom 7, Gus Grissom's, the late Gus Grissom's Mercury capsule, and a number of other things on the seafloor. He's found because he's built submersibles to do pretty fancy sonar for depth and imaging and all that sort of thing. Fluid flow measurement, they can actually tell, sometimes it's hard to measure flow because, as you know, you have to interrupt a conductor to get to measure the current. Although there are some Hall effect sensors now that can measure current, and there's some clamp-on current transformers that can measure AC current. But fluid flow in a pipe, you usually had to cut the pipe open and put in some little turbine mechanism as the water flowed by, or the fluid went by. It spun around a sensor, and that sensor was used to indicate the rate of flow of the fluid. Well, with that Doppler technique, you can drive some energy into the fluid flow, sense it, and detect a change in frequency of your energy, and make an estimate on the fluid flow. And this is used. This is how people evaluate the carotid artery to see how much blood flow is occurring there. And it's also used for fetal blood flow, even in newborns with their tiny veins. They have this technique down so well that they can measure blood flow for in veins or arteries, and then with a little bit of imaging, they can figure out the size of that artery and therefore come up with a volumetric flow rate. Airborne terrestrial surface mapping works very similar to subsurface ocean floor mapping, except it's usually radar, or there's a couple different things. Sometimes they use actually a side scanning radar, but the idea is the same thing. Energy is sent out and then detected in its reflection, and you either get a time of flight, in which case you know the distance to something, or you get with multiple receivers, you get a sophisticated processing and a terrestrial surface model for mapping. Distance estimation in building contractor trades, you can go out and buy these things now that are laser based, and they'll send a little pulse out and they'll reflect back. And I'm going to show you let's see here. I think we have. I will show you a data sheet for here we go. Now here's something where they use a vertical cavity surface emitting laser. It's basically like an LED, except it doesn't produce light with a whole bunch of different phases. It produces coherent light at one phase. It is a laser, and that laser sends out a pulses of laser light and then senses them in a receiver. And they generally make these they make these for various distances, and it's a class 1 eye-safe laser. You can see that all in here. But this VL53L0X is quite a thing, and you can do autofocus because you can measure distance to something. This one says it can measure absolute distances up to 2 meters. I've seen that you can get some of these that are optimized for, say, up to 20 centimeters, and others up to 2 meters, and I think they can even do farther. But the point is, it's a time of flight sensor, and you'd hook this thing up to a microcontroller and you'd measure some time, and here's some applications here. User detection for personal computers, laptops, and robotics for obstacle detection, or maybe safety. Something is moving near an area and you don't want interference either with humans or between mechanical things, and this time of flight could tell you something's getting too close. White goods, hand detection and automatic faucets, soap dispensers, etc. And then this one here, one-dimensional gesture recognition. almost looks like one-digit gesture recognition, which is quite popular with drivers in Massachusetts. They do a lot of one-digit gesture recognition. But there are chips now using lasers or even some form of light, where you move your hand and you can use it to advance the slides on a remote slide projector, or kind of have your hand act like a mouse kind of thing. So that's kind of happening. And laser assisted autofocus, I mentioned. There's lots of things you can do, but ranging to objects. So all the things that you do for industrial control, is an object in the way, or is an object going by on the conveyor belt, or something like that. These things can do that. You could do it with interrupted light, or you can do it with reflected light using one of these sensors. What else do we have here? Just time of flight, distance estimation in building contract trades. I mentioned the kind of estimator things that they have. Contractor can go in and get the square feet of a room really quickly with these things, at least approximately anyway. Cable fault distance estimation. If you send out a pulse into a cable or an optical fiber and you get a reflection back and you measure that time, it's a process called time domain reflectometry. And you could tell if you're making it all the way to the end of the cable, or if there's been a break in the cable and you get an early return. Well, then you could estimate the distance to that break, and that could make repairing the cable a lot easier if you know where to look for the problem. Geological subsurface surveying. You may have seen where people they actually set off a little charge on the surface of the ground, and they lay out a series of they call them geophones, and the energy from the small explosion on the ground penetrates the ground, hits various layers where the rock properties change or whatever. They come up to these sensors and they can get a time of flight and therefore a depth to where the rock changes. But if they do enough of this, they can actually get some subsurface mapping of rock structures under the ground. So again, it starts out simple with time of flight, then you start using more and more sensors and putting them into computers, and you get a lot more. Archaeological surveying, people walk around with ground penetrating radar looking for things that aren't natural, things that are maybe very rectangular or something that look like they're artifacts of some culture. We mentioned industrial automation and motion control. Satellite tracking here is a little weird in that low Earth orbit satellites, because they're going overhead so fast, are subject to Doppler shift. And so sometimes the Doppler shift is actually used in tracking the satellite. Geosynchronous satellites, the ones that are like approximately 22,000 miles out there, they appear to stay overhead, or at least over the equator, and we kind of depend on their position being constant. But low Earth orbit satellites, if they have a carrier frequency where they're transmitting something, we will hear a pitch change as they go overhead. And of course, we can thank the devil himself for automotive speed sensing, radar guns, LiDAR guns, and that sort of thing. And you can think of all sorts of countermeasures to these things, just as military people think of countermeasures to radars and that kind of sensing. I just think it's well, we all have our opinion of the government and how much they should be sensing us. So anyway, that is our that is our discussion on time of flight and sensing applications. And now I'm going to save the PDF, and I will make sure I put the latest one on the website. Couple of other things I wanted to mention. Wikipedia has a nice Doppler effect thing. This is the Wikipedia Doppler effect page, and if you wonder, how does this thing happen? Well, especially with sound waves in air, if someone sounds a note at a fixed position and the observer, say us, is at a fixed position, the sound waves are formed as compressions and rarefactions, and compressions and expansion of the air, of the gas. And so they go out in at a constant rate, and we just hear that rate. But if that source is coming toward us, you can see the wave crests are compressed, and so they come at us more quickly, and we hear a higher pitched note. And as the source goes past us, when we're behind it, you can see that the wave crests are actually expanding or increasing in distance to an observer who's behind the moving object. And so the pitch is lower because, again, as the period or the distance between the wave crests gets larger, frequency gets lower. And when we're in front of it, the period gets shorter, the frequency gets higher. Oops, sorry, didn't mean to do that. So you can look at this stuff, and it even shows you how to compute frequency change. Based on you either being still or you as observer moving and the source moving. But it's pretty easy to observe this. If you see speedway videos or anything and the cars go zooming past you, you can hear that decrease in pitch, especially the increase seems a little harder to hear. But a train whistle or a car going by, you can definitely hear that reduction in pitch as it goes by. So, that is time of flight. Oh, let's go look at our basic program here. So, if you look at this thing, this is our, basic stamp, and this is one of these ping things, and one of these guys is the sender, and one of these guys is the receiver, and I actually don't know which one, nor do I really care. But what happens here is, I don't know if you can see this, there are actually 3 wires down here. There's I think it's like ground +5, and then a data wire. It's sort of like a data wire. You tell it to send out a pulse, and then you take that wire and you say, oh, I want to use that same wire now as an input to my microcontroller, and you wait for the return echo. And these things have been favorites in robotics for object detection, be it obstacles or when you're actually looking for something. And I'm going to go over to, let's see, we'll go over to the Windows side here where I'm running the basic stamp software. There we go. And I think I can raise this up and point it down at the desk. And you don't see me doing that, but right now I'm, let me see. What do I do with my ruler? Well, here we go. So here's my ruler, which you may or may not see. I'll try to get this into the video, but here's my ruler, and right now I'm about 12 inches off the desk, and I'm getting like, I don't know, 900, right? And if I come down to, let's come down to 6 inches off the desk, I'm getting about 450, okay, so like half the number. And if I aim toward a wall, you may not be able to see this, but there's a wall, oh, that's now 3350, that's like 3.5 foot away or something, maybe even 4 foot away, I don't know. So you can see I got a really big number there, 33, 32, 33, 28. The ceiling's up about 35, 60. And so now I put it down here and it's looking at me, and it's I'm about a foot away again, so it's somewhere in the deal. That's my arm getting in the way. So here's our program, which is pretty simple. We have a do loop, and we pulse out here on pin 15. We pulse out with a value of 10, and then we use the pulse in command, which measures the we're going to measure how long the pulse is high. And so we're going to put that in a word variable called time, and then debug home. That just means clear the screen and go to the top left corner of the screen and print out time equals decimal 5 digits time, pause for a second and do it again. And I think the one maybe the one in the book had pause for 100 or something, so you can play with that and try it out. But I found that I was able to the first ping thing I used, I could get to about 14 centimeters, which is not a lot. That's I don't know, it's 10 centimeters is like 4 inches, so it's probably about 6 inches, or something in that area. And it just after that it wouldn't give me anything, so I found another sensor, this one here, and it seems to do all the right things and work for a long distance. So there you go, there's ping sensing, and we'll be talking about keyboard scanning, and we'll also be talking about binary and decimal numbers very soon. So have a great time, and we'll see you again soon. Okie doke, take it easy. Whoop. There we go. All right, so let's